All right. Okay.
All right. I'm going to go ahead and start with the introduction and welcome to all of our students here in the room. We have, can he see? I don't know if he can see the room, right?
No.
Okay. Well,
Yeah.
we have Dr. Joel Bowman with us, and he deals with theoretical studies. So I think he'll be really good at imagining how many students are in the room. And since he deals with theory, okay, so we got, maybe 15 students in
Oh,
here.
great. Oh, that's
Yeah.
wonderful. Yeah.
So,
It's more like 26, unless.
oh, I got, yeah, yeah, there's more.
Oh,
Oh,
wonderful.
more are coming, more are coming.
Oh, okay.
Yeah. So we thank you for joining us. I'll read a little bit of your background in case our students didn't read it, and for posterity for our video here.
Okay.
Dr. Bowman is the Samuel uh, Candler Dobbs Professor of Chemistry Emeritus at Emory University. He got his PhD from California Institute of Technology, and his looks like this bachelor's from the University of California in Berkeley. And he was the chair of the Emory Chemistry Department. Which how long did you do were you chair?
I did 2 3-year terms.
Oh, very good. Oh, so you guys had a rotating.
Yeah,
uh,
we did. We
that's
did.
good. That's good.
Yeah.
Uh, Visiting fellow at Magdalen College, Oxford University, Yale University, visiting professor there, and then also at the University of Chicago. So were you at the University of Chicago for a couple of years,
Um,
or is that a
that was just a visit. That was a semester.
semester? Okay, yeah.
Yeah.
So that we're not too far from the University of Chicago,
Yes,
probably
I know.
2 hours away. So
Yeah.
that's good. And you're an honorary fellow of the Chinese Chemical Society and a fellow of the American Physical Society and the American Association for the Advancement of Science. And those are all very prestigious. And honored by the Festschrift issue of the Journal of Physical Chemistry and an election to the International Academy of Quantum Molecular Sciences and the Dudley Hirschbach Award in Theory and the Alexander von Humboldt Research Award. So definitely you have, it looks like a lot of experience and we're excited about that. And I went to your webpage and was talking about the work that you guys do there. And it's theoretical and computational, looking at various aspects to not just water, but other materials. And that looked quite interesting. And I saw that it said current work was being done on, it looked like acetate, acetate bromine, water clusters, HCl and water clusters, liquid water, hydrated hydronium,
Yeah.
hydrated ion pairs, methane hydrate clathrates. These all sound exciting. And what I was thought was very interesting is your research group with all this theory about water never does anything to get their hands wet. So
Absolutely.
without further ado, though,
Okay.
I want to turn this over to you so we can learn some more things about quantum mechanical aspects of water, what's new. And a question, though, that I want to give you a heads up on that I'm going to ask at the end if the students don't do this. We want to know, because I get asked this all the time, is water wet? Okay, so you've got to answer that question at the
Okay.
end, if not throughout the talk somewhere.
Okay.
We want to know, is water wet? But we also want to know some important things about the quantum mechanics of water. Dr. Bowman, thanks for joining us.
Okay, my
The screen
pleasure.
is yours.
Thank you so much. Wow. All right, this is fun. Um, and I hope it's sort of interactive. I don't know if the students have an opportunity to be heard, but hopefully you are. And stop me anytime with questions or comments. This is supposed to be fun and interesting, not challenging and boring. And yeah, we're gonna keep that in mind about is water wet? That's a good question. Well, let me start off. I've got a sort of an outline of things I want to talk about. First thing is, how do most people think about water? It's so ubiquitous, so important to us, and so we really should address that. Now it turns out water, we all know a glass of water is important, hydration and so forth. There have been some interesting health controversies. So there are what's called homeopathic ideas about water. I'm not going to go into that in great detail. I'm just going to pick on a couple of things just for fun. And then kind of ask the question, how does a chemist think about water? All right, this particular theoretical computational chemist. Um, Now, I assume everybody, the students are all science majors or mostly all
Yes.
science
Yep.
majors? Okay, so you all know scientists have a certain way of thinking about things. And eventually it can be a little challenging to talk to your parents or your friends who aren't scientists about how do science, how do chemists and scientists think about things as common as water? And the good question about is water wet? Quantum mechanics is in the headline, and that's a scary topic to most people. It really is. So I'm not going to go over, everything about quantum mechanics. I do want to talk about what aspects of quantum mechanics apply here. All right. And I think that you'll enjoy that. We are going to look at something called water clusters. All right. And this is very important for a whole lot of reasons. Uh, it's the area where really hardcore physical chemistry, chemical physics, and theoretical computational chemists meet. And we'll talk about that. Also, we'll come back to the controversies about water and water clusters.
Oh, good. Oh, good.
Yeah, it's cool. Then the latest, okay, finally we'll get into a little bit about the latest water model and quantum mechanics. And then I'm going to finish up by sort of, changing gears on you. What happens to water if we add a proton to it? Whoa. All right, it turns out that is a major change. And of course, everybody knows protons and acid, right? Acids release protons in water. And wow, that can really change everything. And how do we investigate that? So I'm going to just sort of end on that. Okay, so let's start. Well, this is one way most people think about water. Take us back to yeah. Oh,
Nice.
now don't we all wish we were there right now? So okay, waves and beach and sand and breaking surf. And it is for me and many people a very nice way to relax. Hearing it, seeing water waves, somehow for so many of us, it's very soothing to see water. Now, water, of course, comes in different phases, right? Maybe this comes back to your question of wet. Now, if we went into that surf, I guess we'd be wet
Hmm.
for sure. Now, that surf is in liquid water. Hey, all right, it's liquid water. Now, water comes in different phases, actually a lot of phases. What you're looking at here is Old Faithful doing its things for the tourists. Now, I've actually seen Old Faithful in Yellowstone National Park quite a few years ago, and I did see it go up. Now, what are we looking at here? What phase of water is this? Anybody?
Students, what phase?
Is it the one to the left?
Yeah, the Old Faithful
Okay.
gas. I'm hearing gas.
It's gas. Some people would call it steam.
Yeah.
For sure. This is very under very high pressure. This is very hot. So this is steam coming out of this geyser. On the right here, this is a real photograph. What are we looking at here on the right?
Yeah, the same phase that we experienced as they walked to the science
Yeah, you
complex.
see this. Yeah, is Lake Michigan part of it frozen?
I think they're starting to see a little bit of ice right now.
Okay.
Yeah, it's been
Yeah.
cold for a few.
Yeah.
Yeah.
All
Yeah.
right. For sure. We know that can happen in Lake Michigan.
Oh, yeah.
So what we're looking at here, basically, whoa, is a real scene. Obviously, the stuff that looks very bright and even blue here, this is ice. And of course, we're seeing water. Now, what are we seeing? What's kind of amazing here that we're so used to that it's not amazing to us anymore. Uh, we're seeing ice. Why? Because it's floating.
Yeah.
Now, turns out to be rather unusual aspect of water. Ice we know is a solid form of water. So we've just briefly, spanned the three general phases: liquid, right, and the vapor, if you will, the steam, and now we're looking at the solid. Now, most things when they undergo a transition from the liquid to the solid become question for you: more dense or less dense? More dense or less dense?
Students,
What do you think?
if something goes from a liquid phase to the
The
solid phase,
solid. Usually what happens?
more dense.
It is more dense, right? So if it were more dense, it's going to sink, right, into the liquid. Why? Because the liquid's less dense than the solid and the okay, that's not happening with water. It's just the opposite. That's why water floats. Apparently, the solid form, which we'll call ice generically, is actually less dense than the liquid. Woo! Okay, so another kind of anomalous property of water that's very important. Okay, so I visited the University of Alberta some years ago, quite a few years ago. I was an external reviewer on a PhD exam, and it was like in the middle of the winter. I was actually, yeah, flying in from Chicago. I was told that there are a lot of different names for snow in Eskimo Inuit. And I'm not going to even try to pronounce these, but you can see. So people who've been around snow and ice long enough and have observed it will know that even sort of snowflakes or ice all can really take on very different shapes and forms. All right. Well, another reason, we're interested potentially in water, and that has to do with its importance in life. And we know that, obviously. All aspects that we can think about could even be, there are theories that tell us that the first life that appeared on planet Earth actually was in the oceans, and that somehow, this is a little picture, possibly how creatures left the oceans and eventually adapted to living outside them. Of course, life lives inside and outside the oceans and the fresh water gets in it. Now, the benefits. So we are about 70% water. Okay, that's a number you can carry around. All right, so this is presumably when you're hydrated well. The body's 70%, and in fact, apparently, I mean, you can see this on the web yourself, different organs and different parts of our body have even more or less water. Look at, our heart is almost 80%. Joints, who would have thought? Joints, 83% water. I guess I'm going to take this to be true. The 70% I basically know is true. Liver, wow. Skin, only 64% maybe. All right, now on a dry winter day, could even be less than that, right? We know that. All right, now what does water do for you? Now this is a pretty deep question, really. And we can get into this in some simple ways. We know it regulates body temperature. At the very least, it's sort of a working fluid in us that allows us, this is how we cool off. And it's one way we maintain our body temperature of about 98 Fahrenheit. And this is a fact. And of course, we know we respire through our skin. And probably that's why the percentage of water in our skin is actually lower than 70%. That's pretty, okay, we know that. That's pretty straightforward. Okay, it forms saliva. Okay, we can believe that. Now, delivering, lubricating joints, maybe a little less obvious. Obvious, like he flushes the body. We understand that. Now, some of these things are a little less clear. I like this acts as a shock absorber for
Hmm.
brain and spinal cord. That's interesting. I didn't know that. Now, its ability to allow body cells to grow and reproduce and survive. To be honest, we really don't know the details there. This is a very complicated problem in chemistry and biochemistry,
Mhm.
down at the cellular and the molecular level, and needed by the brain to manufacture hormones and neurotransmitters. Again, that's very general, isn't it? The specifics of that are really under scrutiny now. We really want to dive in very, very deeply there. Okay, so, right, we know it's important. We know we're made up of it. So let's go from there. Well, since it's very important, you might not be surprised that there have been attempts to identify what we might call very special forms of water that are even better for you than just, what comes out of your tap, right? Or your water cooler. I love this one. It's called Penta water. Now, the interesting thing about Penta water is you can still buy it. I'm not recommending it, but you can see this. I just went online. I can get this delivered free at my local Target by whatever I put this out. Wow, you can get it at Amazon. So, what is Penta water anyway? Hint. Okay, so everybody know the penta is the Greek word for five. You guys all know that, right? Pentagons and so forth, right? Something to do with five. Well, let's come back to that in a second, in a minute. Well, in fact, it was claimed that there were clusters of penta, that there were groups of five water molecules put together. So I guess you'd have to say in a pentagon, maybe, but at least five. And there was a claim that this created tremendous benefits over ordinary water. And believe it or not, this really got the attention of scientists and the press. And indeed, it turns out there was a class action suit in 2013 in San Diego brought against this company for false advertising and so forth and so on. It could no longer claim that it had special health effects. And a colleague I know, UC San Diego, Andy Kummel, very good guy, concluded that Pentawater claims were not only wrong, but absurd. Okay, so here comes the scientist spoiling the fun. Uh, okay, but you can see, you can still buy Pentawater. So there's some more citations of this. Um, it was structurally, there it is, structurally superior to normal water. All right, so we're gonna come back to that cluster actually. Okay, so not to be outdone by pentawater, there was hexagonal water. All right. So hexagonal water, refers to a cluster of water molecules that form a hexagonal shape. Yes and no. We'll talk about that. Supposedly enhancing nutrients and so forth. By that, this is all from Wikipedia. Wow, this went on and on. And of course, totally debunked by science. So there's a whole lot of things that we found that came in here. So one of the first things that we'll get to is how is water, and we'll talk about water, whether it's a solid, a liquid, or a gas, at least a vapor, not just a single water molecule. These are held together by hydrogen bonds. You've all heard of those, I think. We'll say a teeny bit about it. And this is what makes water kind of sticky, all right? Quite sticky. And there we talk about these bonds are continually breaking and reforming. We see this through simulations. And so there's no way that we could ever imagine a water sample that consists only of pentagons or hexagons. All right, it's just patently absurd. So anyway, it took a bit of work. And down at the bottom here, we're going to get into this a little bit, the experimental observation of water clusters. All right, you guys all know a little bit about spectroscopy. I'm going to say a teeny bit about it. were used by some really outstanding experimental groups in the world to really study and go in incredible detail to look at some of these water clusters. Now, water clusters, you might even say, is a fourth kind of water. We'll describe that. Wacky water. Okay, so this came from the New Scientist. There were some very important theoretical and experimental work done on water. Just summarizing what we know: icebergs float. It's weird, hard to heat. Da 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 da. Terrific solvent, etc. It's how does water do it? All right, so clearly that's kind of where the science. So how does a chemist think about water? Now, there's a lot of different ways. We can think about water. We can certainly think about it as a thermodynamics person, heat capacity, boiling temperature, delta H of vapor, blah, 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 blah. We can study it. We can study the thermodynamics of water and steam. And that was really done enormously sort of in the Industrial Revolution when the first engines were steam engines. And so but we're not going to do that now. I would say that's not how a 20th century or 21st century chemist thinks about water. All right, let's start. One of the key tools that people use in studying water is something called infrared spectroscopy. All right, now, very quick look here. So you guys all know that if you shine light on things, green plants are green because they're absorbing the other complementary colors of the sun, right? So things that are absorbing or not absorbing determine the color. And the absorption, all right, we can study this in the lab, and maybe some of you have done some infrared analysis in your PChem or organic labs with an infrared spectrometer. Basically, you've got a sample you're interested in. We'll call that water. And then if we're looking at things in the infrared, all right, that's invisible to us, as you know. But we can do this obviously in science. And we will adjust the wavelength of this infrared source, and we look for absorption. And what that typically means is there's a dip in the transmission. So if there's no absorption, the infrared light just goes right on through, virtually unchanged, flat line. If there is some absorption from a molecule or whatever it is you've put in there as a sample, it gets absorbed, and there's a depletion, right, of the intensity of light. It's that simple. Now, if we look at isolated water, there it is finally, H2O. Everybody knows that. Every small molecule, kind of incredible. How such a small molecule can be implicated in so many things, like, the existence of life as we know it. Now, molecules vibrate. Okay, you can think about molecules as being balls and springs. They really are not just sitting there and stick figures. They're actually moving around. And molecules all have very special kinds of vibrations, kind of like a musical instrument does, right? Certain musical instruments will suddenly hit a harmonic, hit a vibration, and get this gorgeous sound, right? You change a key, a stop or something, and suddenly the sound is different. The frequency is different. Now, water has these three fundamental vibrations, and they're depicted here. The bend, I mean, I could try and do that for you, all right? So the two hydrogen atoms are coming back and forth, and the oxygen is barely moving. That's what this is to indicate, and it's kind of a flapping. And it actually does that at a very specific frequency, such that we can cause that bending to move, like a resonance, like, when you're blowing in a bottle, you hit that right amount of velocity in your breath, and that bottle, will suddenly make a noise. And this comes in, we're going to work in these wave numbers. So it comes in a number. It's like a fingerprint. 1595 wave numbers will get this thing going. Now, there are two stretches in water. One's called a symmetric stretch. It kind of looks like, you're working on a little band stretch, or a little exercise thing. You're stretching back and forth. That comes at a much higher frequency. And then finally, this thing called the anti-symmetric stretch, sort of go in and out like that, right? These are the fundamental modes of vibration of water. And if we had water in a spectrometer, we would see dips in the transmission at these frequencies. Cool. Well, all right. We wrote a paper not too long ago, 2015, got the cover of this journal called Physical Chemistry Letters. And what we're showing on this cover would be the spectra, the infrared spectra that you would see, and we actually calculate, for three kinds of water. The top one, that really looks like you're scuba diving, right? So the top one is liquid water. And bud, there it is in wave numbers. Now, if I were able to scoot over here with my, you'll see there's a little bump there at about 1600. If you go between 1000 and 2000, you see that little bump? Guess what? That's basically the bend, but it's a liquid. And then you go over to see this other big peak sitting there at about 3500 wave numbers. Hey, remember? This is real liquid, but there it is. It's still water, like the molecule water, but it's kind of it's actually a liquid. Now you'll notice there's some other features in this spectrum below 1000. All right, we never see that in isolated gas phase water. That is a signature of the liquid. Going down, ice is shown on the bottom right. And we're looking at in particular at this stretch region. And there's a picture, sort of a schematic of ice, kind of amorphous looking. In fact, it is called amorphous ice. It's got a very broad spectral feature. The other picture you're seeing there is a ring, and that's a cluster. And now this ring it's 6 waters, and they each have their own signature, and they're all perturbed a little bit from each other. They're not identical. And what generates here is, you can see this picture from 3200 to 3800. Woo, all this extra goodies, all this extra stuff. And this is really telling us that each of these water molecules is slightly different from each other. They're not all lined up exactly the same. Well, all kinds of information's potentially in here. Okay, so we've gotten a little look at, one way chemists think about water is through this spectrum. Well, we haven't learned a heck of a lot, I have to say. It's a little bit about spectroscopy, I think, from your classes. Now let's get on to the quantum stuff. So what aspects of quantum mechanics apply here? All right. Now this is interesting. Now, have all of you heard of the uncertainty principles? Can we see hands go up? How many hands go up?
I would say 80% of the hands, maybe 90.
Very good. All right. So this is something we hear about. We see it sometimes in the popular media or something. Now, it's not an easy thing to talk to our friends about. It's actually due to this brilliant physicist by the name of Werner Heisenberg, who won the Nobel Prize at age 81. And it's actually called the Heisenberg uncertainty principle, if we really want to get, sort of technical about it. Now, it's probably the most famous and I would say baffling aspect of quantum mechanics, all right, to explain. Now let's read it. It says something like, and I'm afraid I'm seeing, I don't want to leave my Zoom, so you can read it, all right? But it basically says it's impossible to know both the position and momentum. So you guys know momentum is basically the speed, the velocity of a particle with perfect accuracy at the same time. The more precisely one is measured, the less precisely the other can be known. Okay, that's why it's called uncertainty. This seems really unintuitive, because all the time when we look at the world outside, we see things moving across the sky. We see moving, somebody running by us. We know where they are. We know how fast they're going. You stopwatch, everything's fine. This contradicts that. And what it's saying is somehow down at the molecular level, the atomic level of nature, this applies. So there's a limit where the precision can be taken. It has something to do with the wave-like nature of matter at the quantum level. This begs the question. It doesn't help you at all. All right. Let me try something a little easier. So, what are we looking at here? This is our proverbial water balloon. Okay. So we know okay, we've all held water balloons, right? They are, of course, they are filled with water. Luckily, water comes back here. Now, what do we know about them? They are kind of amorphous. It's a little flexible, right? If I start pushing on it, in other words, if I push on it, I'm going to change it. All right. If I push on a little, whoa, okay. If I push too hard, boom. All right. This thing, it'll burst, much to the delight of the young lady who just did this. So this water thing, can you say where it is? I don't know. What define the boundary? How do you define the boundary of this water? If I start moving it, right? It's like when you're pushing on it, what are you doing? I'm giving it momentum, moving it. By moving it, I've changed its shape, right? And if I go a little too hard, I change it to the place where it'll burst. Atoms and molecules are a bit like balloons. All right, a strange concept, but it's possibly one we can wrap our heads around. So they're not really solid, of course, and they're not filled with water. They're not filled at all. All right, there's a vacuum, but they are kind of like balloons. And again, if you push on them in a certain way, they will move. All right, so it's very hard to get this precise position and speed. If we push too hard, we take a molecule and we really try and compress it, it's going to blow up, actually. So let's get a teeny bit of math here. And what I'm showing you is a mathematical representation of a spring. Right? So this is an OH bond. All right, it's an OH bond. And everybody knows molecules kind of have equilibrium structures. They sure do. Okay. And we call their equilibrium distance, say the bond length. Everybody studies these RE. So RE would be the distance, say, between the oxygen atom and a hydrogen atom in water, what we say at equilibrium, right? Now, the way a physical chemist thinks about this is that there's actually a potential that governs the stretching motion. So the molecule just doesn't sit there like a stick. It can vibrate around. Now, the potential will go up if I pull it apart. It will also go up if I compress it, just like a spring, right? You know that. So at the equilibrium distance, i.e. RE, this potential is zero. It's zero. All right, you're sitting down at the bottom of that well. This violates the uncertainty principle. I'm saying to you, this molecule has a distance exactly given by RE, and it's not moving. Does that violate the uncertainty principle? I've told you its distance is precise, and I've told you its velocity is precisely zero. Does that violate the uncertainty? How many think it violates it? See some hands. Don't be scared. It seems a little weird.
We got a few hands up. Yeah, maybe half.
All right, this doesn't sound right. I mean, this doesn't sound right. Molecules, but it does. No, sorry, it does. What I just said, it has this exact separation of RE, so it's just sitting there and it's not moving. So I know exactly that distance, and I know that it's not moving. It does violate the principle. So, Heisenberg comes along and says, you know what? The reality is no molecule can sit at the bottom of that potential. No molecule sits at RE. What? I'm contradicting so much of what we learned in chemistry, aren't I? We keep, and it's okay. All right, it's okay. But the uncertainty principle says, no, I can't do it. There's got to be some trade-off here between the position and the momentum. It turns out there is. There's kind of a minimum value that these two quantities can have, and just satisfy the uncertainty principle. Now, the uncertainty principle, I gave it to you in words. You got to be able to write it down in math. And that's what Heisenberg did. Brilliant theoretical physicist. He actually wrote down some equations for us. And these equations actually help us, they address the question of what is the minimum amount of energy. So it can't be zero. The molecule cannot sit down at that minimum with no velocity. No. If it did, its energy would be zero, absolutely zero. Nope. But there is a minimum energy that it has to have to satisfy the uncertainty principle. That's called 0-point energy. Let's see hands. How many of you have heard of 0-point energy?
One hand.
All right. Now, how many of you think you understand what it is now? Let's see hands going up.
You guys think you understand what it is?
It's getting there. All right. There's
Got a few hands. Yep.
All right. So it's really amazing, and this is one of the most profound consequences of quantum mechanics is that in fact, things have to have this minimum amount of energy. It's called 0-point. Now, okay. There is more to this in quantum mechanics, and I'm just going to introduce another famous name. So you've heard Heisenberg. How many of you have heard Schrodinger? The name.
Yeah, most hands are going up here. We've heard
All
the
right.
name. Yep.
Everybody's heard of Schrodinger's cat, or at least. Now, Schrodinger actually gave us a way to get really detailed information about this 0-point energy. All right. He knew all about it, of course. And in fact, he gave us a procedure that allows us to actually calculate it. So how do we calculate this 0-point energy? So we make Heisenberg happy, all right? We make Heisenberg happy, but we're now down looking at every specific problem that we're interested in. There's a different 0-point energy, okay, can be. Oh boy, partial differential. This is called the Schrodinger equation. Whoa, okay. Psi zero is called a wave function. You guys have heard wave function, I'll bet. All right. You've heard Schrodinger equation. Now, whoa, this is a partial differential equation. Whoa, we're not going there. It's not easy to solve, but we can do it now quite amazingly on our very, very powerful computers. We have to do it numerically. And this is an example of some of the computer clusters I work on at Emory University at the Emerson Center for Scientific Computation. And these massive computers, Google uses these a lot and really help us solve these equations. And I'm not going to give you any more on that. But I want you to keep in the back of your mind this business about 0-point energy. Okay, now let's take a look at water clusters. What are they? What do we learn from them? Well, hey, there's Penta. Okay, I told you there is actually a cluster of 5 water molecules. And guess what? They do join up. There it is. There's the picture. They do join up, and the dotted lines here are what we call hydrogen bonds. So you can see there's a hydrogen atom that's sort of donating, apparently it's bonding up to the oxygen of another water molecule. That's called the donor hydrogen. And the acceptor water is on the right. And it just goes around beautifully symmetrically. I probably screwed up there. There should be 3 dotted lines. Sorry, you're only seeing 2. Well, that's penta water. It exists, and we can really study it. Now, you can see hexagonal water? Can you see it? Or is it obscured by the gallery?
We see it.
Good. Okay. So there, look at that guy. That's really hexagonal water. Now, actually, it's called a prism. So the word we use for that is prism. I guess it looks kind of like a prism, right? And if you study it enough, it really is like two planes, two trimers. So three waters on top, three waters on the bottom, if you see that, right? And then they're all connected with these hydrogen bonds. Wow. Wow. So are these things for real? All right. Are they for real? And, can we actually observe them in the laboratory? Well, the answer is yes, both is true. They're all observable, not easy. Now, the other thing that is so cool, if we go back to the hexagon, it's really cool, like Tinker Toys. Well, it turns out I can connect these six waters in a lot of different ways, which will work out somehow. So the number one is called the prism. That's the one we've already seen. Pretty, isn't it? Very nice. Number two is called the cage. All right, maybe that's a little harder to get your mind around. Very different form. And I've got other things called, the book, the ring, and there's all these colorful terms. So there's a bunch of these, okay, that exist and that actually have been, well, studied. Now, the smallest, let's step back for a second. What's the very smallest water cluster that can exist? Well, that's just two water molecules, right? That's two, and it's called the dimer, the water dimer. And I've put a boundary. There it is. Beautiful. Stare at that a little bit with me. So you can see this is, three-dimensional, right? One of these waters is twisted around, the one on the right. The guy on the left, there's still water, but the guy on the left is actually donating a hydrogen bond. So we're making a hydrogen bond. So this is, in fact, the equilibrium. We'll come back to the 0 point. This is the equilibrium structure of this water dimer, all right? And that hydrogen bond, we know its bond strength very well. What I mean by that is how much energy does it take to break that bond, that hydrogen bond? We know it exactly. And we've tested it. So this was an example of, just to give you guys an idea, the way we make the best progress in science is when theory and experiment come together. All right, there's a gorgeous there's a beautiful, sorry, I should say, experimental work. This is shown here. This is the low frequency spectrum of the water dimer as a sensitive test, blah, blah, blah. And the experimental group is Martina Havenith, that's the last name there, from Bochum. And she did a most amazing experiment that required what's called a free electron laser. I don't want to go into details. I'll show you a little bit later. Just an incredible experiment. And then a bunch of us, including me, did sort of the theory on this, and we were trying to match up a bunch of things. Well, it turns out we just did the same thing with hydrogen disulfide. So is there hydrogen bonding in this guy, H2S? It turns out maybe. It's an interesting question that came up in the literature. And again, we got together quite a few years later. This just came out in 2024 in Nature Communications. And again, a collaboration with this marvelous group in Germany. And there it is. I'm absolutely not going to go through the details here. But again, this incredibly detailed experiment. And by the way, it was spectroscopy. It was a spectrum. And then we're able to interpret the spectrum using our tools of theoretical computational chemistry. And then we can hopefully get them to match up, talk to each other, shake hands. And if they do that, well, of course, we're real happy. And then we can go ahead and make some interpretations of what we're seeing in the calculations. Okay, back to this. All right, it seems like I'm not letting go on this, am I? So the uncertainty principle and 0 point energy, they're two sides of the same coin. Now I showed you this picture, beautiful picture, the prism. No, we're back to where we were before. All the OH bonds are at the equilibrium value, and they're just sitting there. This thing's not moving. Violates the uncertainty principle. Now, next time you have an organic chemistry class and your professor shows a picture like this, you just say, hey, but wait a minute, doesn't that violate the uncertainty principle? Don't do that. Don't go there. But you'd be right. You'd be right. Now, this is in fact the correct picture of the water hexamer. On the left is the prism. On the right, actually, the cage exists too. And this was published in the JACS as a communication. Now, what are we looking at here? Remember the balloons. This is a picture of the wave function. This is a picture of the exact wave function corresponding to the 0-point energy. And what you're looking at here is the motion, a representation of each atom. And you can see these hydrogens are, I call them like mushrooms, or they're pretty big, but the oxygens also, you can see, hey, there's my balloon. So these are fuzzy. These are balloons. They're not those little beautiful dot structures that I showed you, right? And this took a lot of work to get this, needless to say. Okay, I don't want to go through the details, but we can do it. And it's very important for us to do it and to take account of the 0-point energy. It's big. The 0-point energy is big for these clusters. It turns out it's actually bigger. It's a bit bigger for the prism than the cage. So even though the prism is lower in energy, strictly speaking from the potential point of view, than the cage, if I add this minimum 0-point, it goes up above the cage. So then the question is, in an experiment, which one of these will I see? It turns out it's the cage. Even though, so theoreticians were embarrassed because they had calculated the electronic, the energy, the bare energy of the prism was lower, but somehow the cage, but then when we put in the 0-point energy correctly, it all worked out. All right, so we were very happy. Or they're almost the same. Turns out they're both there. All right, another spooky thing. I would need to talk to you about quantum mechanics. Let's go back to the dimer. All right. There's the geometry of the dimer at equilibrium. All right. You can see it, looks similar. Now that's on the left-hand side of there. What am I showing you on the right? Well, looks like I've flipped, right? The H2Os have flipped. You can see this is on the so-called acceptor. Those two hydrogens went from up to down. That's all that happened, right? That's what this picture shows. Well, guess what? Those are exactly the same in energy. You can almost intuit that. They really wind up being exactly the same. There was a flip as well, all right? So there was a rotation. This is a geared thing. So the first monomer flipped up as the other guy came down. This beautiful dance that takes place, and they wind up in the same spot. Two equivalent structures. Schrodinger cat? Is this a Schrodinger cat problem? Well, it is. So I'm going to show you again a picture now that describes this duality. This is a potential. It's a funny-ish looking potential. We call it a double well. The bottom left, the minimum there corresponds to the water dimer I just showed you. But there's an equivalent water dimer structure on the right. It has to do with some of this flipping around. And, well, it's identical. So when I'm thinking about the water dimer, now it gets even spookier. It's not just the 0-point energy that I have to add, right? But I have to take account of, my gosh, which water dimer is it? Is it the guy on the left or is it the guy on the right? And you can imagine this has occupied chemists for a long time figuring this out. And it is a Schrodinger cat. Okay. Now there are ways to see this indirectly, experimentally. I don't want to take you through the details, but Ah, okay, there it is. Okay, so a lot of spooky stuff, even in these very small clusters of water. There are now models of water, liquid water, 1,000 water molecules, really high quality models that have taken 15 or 20 years of effort to put together. I don't want to go through them with you, but basically think about the water as just an enormous cluster. So the little things I've said to you about the clusters, they do carry over, whether it's an ice or whether it's liquid. And in fact, we can calculate the spectrum of water. So go down bottom right, this is a snapshot of of a box, let's say, of water. These are there they are. And of course, they're really moving and grooving, right? We're not going to violate the uncertainty principle. These guys are actually moving around a lot. Can I actually calculate that spectrum and compare it to experiment? And the answer is yes. And that's what I'm showing you on the top two plots here. And, it's not perfect, right? It's not perfect. No, the experiment's right. The theory, it's darn good. Okay. It's about as good as we're going to get because we had to include several hundred water molecules in our simulation. And we had to run this at 298 Kelvin. Wow. Now, the other cool thing is you can deuterate. Well, how many of you have heard of heavy water?
Heavy water. Yep. Most of them.
You've
Yep.
all heard of it. So
Yep.
it's just D2O. And yeah, by the way, you can make it. It's actually in it's in Lake Michigan. You can take a couple gallons of Lake Michigan water and separate and bring out the D2O. All right.
Fun.
And then you can put it in that spectrometer and you can do the spectrum again. And there it is on the left. And again, you can do the theory and the experiment, and golly, it actually looks even better. Look at how nicely I got it to agree. But the two spectra are really shifted from each other, and I'm showing you down at the bottom. The D2O is really shifted, right? Compared to the H2O. Hey, that's cool. That's cool, If I have a sample of water somewhere and I don't know if it's heavy or normal, I can run a spectrum and tell you. I can tell you right away which it is. Now, why is that important? Well, needless to say, when we look for life outside the Earth, one of the first things we look for is water. How many of you have heard this? We're looking for water on Mars, right? Oh, gosh, yes. And in fact, people were looking for water on the moon. Seemed like a very unlikely place, right? Dark, cold. But in fact, there is ice on the moon. It was discovered by this infrared spectroscopy. This is a Boeing 747 called SOFIA, and this was an experiment funded by NASA. And the goal was to get above our atmosphere for as much as we could, get rid of, the interfering water, get out there and perform an experiment. And by golly, this was reported in a nice, I think it was 2020 or 2018. And what you're seeing in this spectrum, there it is, right? It doesn't matter. This is emission or absorption. It's basically the same thing. We're getting signatures. And you see this kind of jaggedy peak at about six micrometers. Guess what? That corresponds to the bend. All right. That's the bend. I said before, 1595. That's the bend of water, H2O, very, very fingerprint spectral signature there. Based on that, they could say, oh, yeah, there's water on the moon. Make the headlines. So there is. All right. It's ice, of course. Okay. Almost done. I just want to now tickle your brains with the final topic. What happens if I add a proton to water? Whoa. Now, again, as a chemist, the experimentalists and the theoreticians are asking, what's the smallest example of this I can imagine? Well, this is basically the smallest example. take the water dimer, as you can see on the upper left, and just see what happens if I add a proton to the water dimer. So there it is, all right? H2O twice, that's the dimer. There's the proton. And I'm having such a great time, I'm not even watching the clock here. Yeah, not bad, not bad. Well, there it is. Look at it. It's on the left. It's beautiful. The proton wants to be really close to water. We all know that. Sometimes how many of you guys have heard of hydronium, H3O plus?
They better all raise their hand.
All right. So you know what that is, right? Now, H3O plus is around. It's called hydronium. But imagine if I got two waters like I have here. Wow. How can I decide which water the proton wants to be close to? Guess what? The answer is I can't decide. I'm going to be in the middle, literally right in the middle. Now, 0 point. All right, we'll get back to 0 point. Now, there it is. Now, let's ask the question. All right, let's pull it apart. Pull this guy apart. This proton is going to make its mind up. Now, again, it's a Schrodinger cat. It's going to have to make its mind up. Which water am I coming out on? And, guess what the answer is? Flip a coin.
Yeah.
The little picture here is showing it coming out on the left. All right. And then if I separate these two oxygens by 3.4 angstroms, that's what this looks like. Hydronium on the left, water on the right. All right. Now, of course, I can bring this back together and try again. Let's suppose I just do this in reverse. I bring it back. Now, that is an interesting barrier. This proton is kind of stuck. It's a little hard for it to get to the other water. But if it hits that magic configuration on the left, you're back at equal 50-50. Pull it apart, and guess what? Do it enough times, half the time it's going to come out on the other water. All right? Got to. So this is called Zundel, named after a scientist who postulated or basically argued that this would be the structure. Now, I'm going to end up with some experiment, and we'll stop soon. How the heck can you study this Zundel cation? Now, we're going to try and do spectroscopy on this, same way we did it before. Problem is, you cannot put this into your spectrometer. You just can't go off the shelf and buy H5O2 plus. Sorry, can't do it. But what you can do, and Mark Johnson is famous for doing this at Yale University, he found a way using what's called a supersonic molecular beam. There's a picture of it down at the bottom. Wow, a typical very high level PChem lab. Lots of electronics, vacuum tube. Oh man, this thing is really, really crazy. I never get close to this. But what this thing can do is it can actually make H5O2 plus. It's just incredible, all right? Now it does it, and then he does something even stranger. He adds a neon atom to it. All right, now this is really weird, right? This is called messenger spectroscopy. It's a very different kind of spectroscopy. You won't see this in your organic lab. So it turns out if you make this beam really cold, I mean really cold, like 20 Kelvin, these neon atoms will stick to H5O2 plus, and he's proven that he's doing that. And on the upper left there, that's a picture of the hydronium of the Zundel, and you see it wants to stick to a hydrogen atom. We know that. So it does that. Okay, now I've made this. I know what its mass is. It's huge because it's the neon atom. Now what he does is he now shines infrared light on this crazy complex. Now it's very weakly absorbing because he hadn't made a lot of this stuff. What he does, though, if there's an absorption of infrared light, it will be enough energy to kick off that neon atom. Because why? The neon atom is just barely bound. It's a rare gas, right? Shouldn't be bound. Everybody knows from freshman chemistry, rare gases don't bind to anything. Well, they'll bind, but not much. So if there's an absorption, whoa, energy goes up. We've got now enough energy to kick that neon atom out, and it will. It will kick the neon atom out, and he measures this. He can measure this coincidence of scanning the laser frequency and the appearance, if you will, of the neon atom. Unbelievable. And having done this, he can generate an experimental spectrum shown at the bottom left. This doesn't look anything like water. Trust me. There's a super intense peak there at about 1,000 wave numbers. Now, there's nothing in the water spectrum like this. Doesn't look anything like water. So what's this? This is a proton, what we call a proton transfer, or sort of a rattling motion. So go back to this proton sitting in the middle and just imagine it's sliding back and forth on a wire and it's vibrating back and forth. Boom, 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 boom. Rattling. That is the motion corresponding to that peak. How do I know it? Because I can do a calculation on the top. Unbelievable. All right. The agreement with the experiment is spectacular. This was done by a group in Heidelberg. And when this came out, people were just thrilled because now we could figure out what's going on with this experiment. So we went up higher, and I'm going to finish. More of these clusters got formed. Add another water. All right. You could make actually what's shown on the left there, this, and so forth. I don't want to take you through the details. So let me finish by saying winter there. This is what winter here looks like on the top. I'm near the Potomac River here in. I had to add to your map, so I'm in Alexandria, Virginia right now, actually. And there you are, and that's kind of a winter scene. It's pretty realistic. And I just gotta. I mean, I don't know. Is this a reasonable enough shot of, I guess, what the winter might look like on a nice trail in Berrien? Do you guys go cross country skiing there?
Quite a few people do. I'm not sure
Yeah, I'll bet.
too much. They're
Well,
into probably ice skating and snowboarding. I don't know.
wonderful. Well, that's how you enjoy the winter weather. Well, thanks again. End of talk.
Thank you so much. All right, we're gonna open it up for some questions. I hope we've whet your appetite.
Okay.
Some information here. Do we have any students to lead us off here? Of course, I had my question. Has anyone asked you that if water was wet? It's sort of a high school student kind of question.
Well, I have to ask you, what do you mean by wet? So what you mean is liquid. So we could say water is wet because it rolls off, it doesn't stick to me really. It rolls around.
Oh,
And
yeah, I've had high school students,
yeah,
basically they will say, well, water can make other things wet, but can it make itself wet? I guess this is the yeah.
yes. So when we say it makes other things wet, with that's just another name for that. It's called hydration.
Mm-hmm.
So water will stick to other things. Obviously, protons and water really like each other. Water will stick to many things through hydrogen bonding. Very, very important type of bonding. And I think, we pretty much understand what it is, but there's still a lot, there's still some discussion about it. It's not a chemical bond. It's stronger than what we typically would call a non-covalent bond.
Okay.
And it's somewhere in between.
Okay.
But it's that hydrogen atom, is the smallest atom. Only got one electron, and it sometimes happily shares it with other more electronegative atoms. So,
Okay, that's good. What kind of questions? Okay? I can wear it.
So is there a connection between
ethanol is a lot of hydrate, many, many things all in one. Yeah.
Okay, Dr. Murray has another question for you here.
Sure.
So is there a connection between the 0 point energy and absolute zero?
Yes, absolutely. There is. So at absolute zero, everything is in the 0 point energy. So it's not as though it has zero energy, but it has its 0 point energy. So if you guys, I don't want to twist too much here, but you guys know thermodynamics a bit, right?
Yep.
A little bit of thermodynamics. And sometimes we count, you know, the enthalpy, we sometimes talk about the energy, the delta H and the delta E.
Right.
Well, at 0 Kelvin, they're not the same.
Huh.
Yeah. So you can think about E or delta E as being that bottom of the potential, right? The bottom of the potential. But it's delta H, which is the E plus the 0 point energy at 0 Kelvin. So at 0 Kelvin, if we want to calculate the delta H of any chemical reaction or any phase transition at 0 Kelvin, and if we want to do it correctly so that it would compare with experiment, if we could do an experiment at 0 Kelvin, we would have to include the 0 point energy to get it right. And we know that is true. The universe has 0 point energy. You sometimes hear the cosmologists tell us that. You know, a vast amount of energy. You can't use it. All right. But can't go below 0 Kelvin. But at 0 Kelvin, there has to be 0 point energy still. Otherwise, we'd be violating quantum mechanics. So to the best of our ability, to the best of our knowledge, quantum mechanics still works at 0 Kelvin. And the 0 point energy is the energy. All right. It's not zero energy.
Students.
So, I mean, that
Oh.
that tells us that in nature, in the universe, there is no such thing as something without energy. Is that one of the logic?
That's right. That's right. That's right. So 0 point energy, you know, in some science fiction stories, you sometimes hear about fluctuations in 0 point energy. There's fluctuating energies, and some people have argued, and this is really rigorous. The spontaneous creation of particles or photons has to do with what's called the 0 point vibrations of the radiation field. Whoa, now we're getting up there into the high energy theoretical physics,
Right.
cosmology, but indeed that's in there. Yeah, so there's a lot of percolating going on actually in the universe, even at very, very cold temperatures.
Yep. Okay. Do we have another? Okay, back here. So come on up so you can hear you.
I had a question about the pent water from earlier. So what are like the benefits for like if animals use pent water? Would that benefit them in any way?
Well, pentawater was a kind of, if you don't mind me saying, fraud is not quite weird. There is no such thing as.
What was there? So I guess the question is, what were they? Because I've heard a lot about,
Yeah.
this water has water clusters.
Right.
What's
Probably anything.
benefits?
So that if you go back, I can say, so go to Wikipedia or something. So the enhanced performance, anti-aging, you know, all the wonderful things. By the way, you know, water does incredible things for us. We all know that, right? We have to hydrate. If we don't hydrate, but there is no penta water, first of all. I wish that, you know, we would like to hope there. So unfortunately, there were some claims, made about that, that just couldn't hold up to science. Sorry about that.
So, what about alkaline water? Have you had some discussions about the health benefits of alkaline water? This is one that I get asked a lot about.
You do. Well, you know, I'm too far away from that field.
Oh, okay.
Yeah, now you got to get in, you know, physiology and questions. And I assume that's all been looked at. I don't know. Some of this has to do with absorption. We've got to get water where we need it, right? So we drink it. It's got to go. It's got to get absorbed by the blood. There certainly could be aspects of water that help or hinder, right, the absorption of water into blood. Now that is clearly going to be a complicated process. You get it. You got that. But basically, the blood is carrying is what is carrying our water around. Getting it in there, is a detailed problem in, sort of biochemistry. Some people think, right, having ions helps. Um, water also we know is very important in transporting ions, and we know ions, potassium, sodium, very important to functioning muscles, let's say. And they get there basically through water. So water brings those ions in. Many. Okay, so yeah, getting into the sort of the physiology of what does water do for us at sort of the molecular level is still a pretty hot research topic. I just want to tell you one thing. I don't know if this has anything to do with 0 point energy, Desmond, but folks, what do you think would happen if you drank D2O instead of H2O?
Ooh.
Don't recommend it. Hint.
Yeah, you will slow down some of the biochemical processes.
So yeah, Dr. Murray is saying you probably would slow down a number of the biochemical processes,
And
and that would probably shut you down eventually.
you got it.
Yeah.
It's toxic.
That's amazing.
Isn't that amazing?
Yeah. One
It's
extra
true.
neutron.
It's absolutely, it's true. It's true. So there you go. And now yeah, right. So what's the difference between, well, of course, there's a mass difference. D is twice the mass of H, right? There's some of it has to do with transport, has to do with diffusion, blah, blah, blah. There's 0 point energy. Absolutely. A big change, a big drop.
Yeah.
And Desmond, you're probably right. The rates, some of these very important rates of our metabolism will get really slowed down. And you're right. If it gets too slow, boom, we can't function. We're little engines, right? Got to stay at 98.6 plus or minus a few tenths to keep ourselves going.
Well, maybe one last question here that I was thinking about. So water has so many of these anomalous properties. Obviously you mentioned the liquid, the solid phase floating, and is there one from a quantum? Is there an anomalous behavior from a quantum chemical perspective that you could share?
Good question. There's not a simple answer to that. Yeah, that's a very good question. Is it anomalous that it has 0 point energy? Yes. If it didn't have 0 point energy, it wouldn't be water. So, but you could say, well, that's not what I really mean. I mean, something like its diffusion constant. Well, it turns out in the bulk, there are some quantum mechanical effects that we see. All right. Now, are they dramatic? It's a good question. And we're unfortunately, or fortunately, we're just at the point where we can actually start to ask those and answer those questions.
Oh, well, that's interesting.
You would think we're just at the point now where we can really trust these very high level simulations, calculating, the delta H of vaporization. Sounds pretty boring. Can that be anomalous? Well, if you don't put 0 point energy in, you're not going to get it right.
Yeah, right there you go.
So yeah, I mean,
maybe the answer.
It's everywhere. So it's not anomalous. The quantum is normal. It's anomalous. Right.
Well, that's pretty good. I think we're nearing the end of our time here. The students have other activities to head to, and it's always great to hear more about water and actually hear about theoretical computation. This is a very big and important field that works hand in hand with the experimental groups, and so it's great to hear what you're doing and how that applies to research and to our understanding of water. And it's amazing that one of the smallest molecules, in the universe, can cause so much research to happen and
It's
take
truly
place.
incredible. Yeah, absolutely. Yeah. The molecule of life for sure.
Yeah. Well, thank you for your time, and I enjoyed hearing your presentation. And let's give them a round of applause, students, if you want.
Thank you very much. Thanks for the invitation again.
Well, thank you so much. And I think Dr. Murray will help navigate, or we could probably just exit now. Yeah.
I'll let you do that. Okay. Bye-bye.
Thank you so much. Have a good evening.
Bye. Bye.
Bye-bye.
Bye.
So let's just end.